Hi everyone, today we're presenting our senior design project, Agile Humanoid Loco-Manipulation with extended sensing capabilities. I'm Zimen. Now I'll be presenting with my teammates, Daruf, Zachary, and Li Yuan, advised by Dr. Zhao and Dr. Linterman. So why does this project matter? Modern robotics increasingly relies on data. The more diverse and rich demonstrations you can collect, the better your robot learns. But when it comes to humanoid data collection, there's a real gap. If you want to capture high-quality human motion today, you need a commercial motion capture system like OptiTrack, which costs at a minimum $5,000 and can go up to $100,000. On top of that, existing datasets like AMAS only capture one type of data, body motion, with no vision, no touch, nothing about the environment. Most existing approaches focus purely on replicating motion, but true autonomy requires more than that. A robot needs to understand the environment, what it's touching, what it's seeing, how forces are distributed. That's the gap we're addressing. Our solution is a multi-modal data collection system built for under $679. You can see the main components here. The dataset is a MetaQuest 3, $299. The onboard compute is a low-cost single-board computer, $150. And the custom compiling gripper, which includes a motor and customizable end effector, comes to around $230. One of the most important design decisions is that the human operator and the robot use the exact same gripper. This isn't just an engineering convenience, it directly reduces the cost by eliminating the needs for separate hardware and ensures the data captured from the human maps cleanly onto the robot. The system is currently developed and validated on the Unitree G1, but the architecture is modular and portable. Deploying it on different humanoid platforms is straightforward. Here's the full system overview. On the left, you can see the data collection hardware, the gripper assembly with a VR controller, actuator, tactile sensor, compiling gripper, and the onboard compute. The middle section shows how data flows. We support capturing in 3 different modes, and the 3 different modalities of data collected, pose and velocity, tactile and vision, are processed synchronously. Critically, before anything gets stored, each stream goes through a series of active quality checks, online retargeting verification, rate checks, timestamping, and multi-camera synchronization, to make sure only clean, robot replayable data makes it through. On the right, data is exported into Foxhub visualization and deployed back into the real robot. Let's look more closely at the hardware. The gripper captures 4 types of sensing inputs simultaneously: VR controller for pose, a camera for vision, a tactile sensor for pressure readings and force estimation, and a motor for position, velocity, and torque. Because the human and robot share the same end effector, the gap between what human does when the robot needs to replicate is significantly smaller. There is still some friction in the retargeting process, but the hardware itself closes a large part of that gap. The sensor modules are also swappable, so you can customize the gripper for different tasks without redesigning the whole system. We support 3 ways to collect data, and the videos here show each one in action. First, direct. The human operator wears the gripper and performs the task themselves. Second, kinesthetic. The human physically holds and guides the robot's gripper through the motion. Third, teleoperation. The human uses a VR headset to remotely control the robot. Each mode captures the same synchronized data streams, giving flexibility depending on the task and safety requirements. One of the long-standing challenges in humanoid learning from human demonstrations is that replaying human motion on a robot is not straightforward. Humans and robots have fundamentally different kinematics, joint limits, and movement capabilities. A motion that's natural for a human arm may be physically impossible or unsafe for the robot to execute. Our system addresses this directly. As data is being collected, the pipeline performs online retargeting, continuously checking whether the captured motion is actually replayable on the robot, and flagging or rejecting data that falls outside the robot's feasible workspace. On top of that, the tactile images go through denoising and contrast enhancement. Camera images are brightness adjusted and synchronized across both burst cameras, and everything is timestamped and rate checked before being stored. The result is a dataset that's clean, synchronized, and robot-ready for the moment it's recorded. Once we have the data, we use it to train a diffusion transformer, or DIT, which is an AI model that learns to imitate and generalize what the human operator does. The inputs are 3 token types: pose tokens, tactile tokens, and vision tokens encoded from the observations. These are concatenated and fed into the DIT, which predicts the next action, arm positions, applied force, and base walking velocity. Those outputs are dispatched into 3 parallel controllers: inverse kinematics for the arms, an admittance controller for compliant torso and end effector behavior, and a reinforcement learning controller for the legs. Then the upper and lower body act together for true loco-manipulation. Here's our key specs. End effector tracking accuracy is some 5 cm when stable. Camera data runs at 60 fps, tactile and pose at 90 fps, end-to-end latency some 100 milliseconds. The retargeting pipeline runs at 90 FPS. Policy executed at 200 Hz. The system runs for about an hour per session. The gripper weighs 420 grams, and the total hardware cost is $679, a fraction of commercial alternatives. To wrap up, we deliver a $679 multi-modal data collection system that meets all our core specs and works with a real humanoid robot. Going forward, we want to make setup faster, improve operator feedback, push the cost even lower, and most importantly, collect enough data to achieve what this project is truly aimed at: agile humanoid local manipulation with extended sensing capabilities, deployed not only on Unity G1, but on any robotics platform in the future. Thank you for listening.